If you are in engineering or similar fields, have you ever seen these people? They would just read a random research paper and they're like, oh, this is not that bad, it's pretty straightforward. And then they just peacefully implement the paper and then move forward. I've seen a few people like this, especially in the grad school. Obviously, when they publish research papers, I was stuck with the old paper because I was a math illiterate. So I asked these math geniuses how they would read the math. For example, I understand what is sine and cosine, but I had zero idea why the paper using sine, sometimes cosine, that kind of thing. So I was like, how do you read and understand? Do you kind of run this mathematical animation simulation like 3B, 1B in your brain when you read them? And then their answers are like, stick to the definition, then everything is clear. Or they said, I don't always animate or simulate any geometries in my brain. And after listening to their answers, I got even more confused because I could not see what they were talking about. And as some of you might know, I even failed my linear algebra when I was a sophomore, and I went to grad school somehow, and not surprisingly, going through this engineering grad program wasn't easy. And here's what I got. I still do not love math, or I didn't say I'm good at it. But now I kind of understand what these math geniuses told me. Just stick to the definition, or you don't have to always animate the simulation in your brain. Or I even kind of see why people say math is just like another language. And now I know I'm not the only one who feels like a math illiterate as an engineer, and probably you are not alone as well. In this video, let me share how I made a breakthrough as an engineer to understand the math. After watching this, hopefully you can also understand what these math literates said from my grad school. So let's talk about it. And if you're new to here, my name is Elliot. I'm a robotics engineer, educator, and entrepreneur providing related services. So in short, you don't have to be a math major to understand math or robotics research paper or textbook, because you will be one in a way. I'm just joking. Do I think I'm good at math? No, I'm still an humble engineer, I believe. But here's my point though. Do you remember that at the beginning of the math geniuses I met? They said the two things. First, stick to the definition. Second, they don't always have to animate the geometric simulation like 3B, 1B, which is very good. But in practice, you don't always have to. Let me break it down. The first point, I really wish I had this understanding before I dropped my linear algebra during my sophomore year. So at the earlier chapters in the textbook, they talk about this vector, dot product, and cross product. Then I asked the question, why are there two? What's the difference, right? Then the most of the answers I got from the class is like, one has sine and another has cosine. Yeah, I can see that, but why? Why are they useful? How are they used in practice? And then the answer was like, you can calculate the angle between the two vectors, but to do that, you can just use either one. Why do I want to use one of them? Then the final answer is like, the exam question will ask you specific vector product, so you don't have to worry about it. I'm like, OMG. I just wanted to know as an engineer when to use which product, right? I wanted to know the practical use case for this, but I could not get the answer. Then I started to lose motivation to study, and that was the moment when the entire math class became a mental labor class to practice my patience. And then I failed all the homework questions and quizzes and midterm. Then I got more demotivated and scared, so I eventually decided to withdraw the class. I just wanted to have a motivation to study the math, like in this linear algebra course, but I was quite frustrated at the moment. But now I have found a way to study math as an engineer. Don't get me wrong, I'm still not that big fan of math, but at least I think that this method helped me understand the math better as an engineer. So let me show you a very simple example that have helped me in my linear algebra course. So as an engineering student, I think it's super important to find the use case of the math concepts, whether it's simple or complex. So let's think of this simple case. There's an airplane. Now you want to know the pitch angle of this airplane. One very popular trick is using the accelerometer sensor, which measures the gravity on the airplane's axis. Then by comparing this reading with the gravity, you can calculate the pitch angle. How? Using a vector product. Now, as you have seen from textbook, there are two vector products. For sure, using one of these, you can calculate the angle, because we have one vector from the accelerometer and another vector that we all know for the gravitational vector. Now, which vector product would you use to calculate the angle? Well, the answer is the cross product. For me, I found this by actually implementing it in Python, and I saw the error that didn't work. And here's why these crazy math geniuses said stick to the definition. If I look at the cosine and sine graph, it looks like this. cosine is mirrored by y-axis by going to the left or right, the y values are the same. But for sine, their signs are opposite, the y values I'm talking about. So to be able to measure the pitch angle of the airplane, like nose up or down, we need to put plus or minus sign to describe the pitch angle, because plus pitch angle means the aircraft is probably climbing and vice versa. Also, in terms of rotation from the freshman physics, the rotation is represented by grabbing the axis with the right hand. Then we can imagine if this is plus or negative rotation. The vector cross product gives us a new axis like this, therefore, in this case you want to use the vector cross product. And this is why they mean by stick to the definition. If you know the definition of sine and cosine like this, choosing cross product over dot product in this case is self-explanatory. Now let's think about the second point that the math literates said. They don't always animate the simulation. An example can be this, the rotation matrix. So, as a roboticist, you want to describe the position or velocity of your robot. Why do you want to describe it? Because you need to write the code in your Arduino or other embedded system or Python, whatever that is. For instance, if you need your robot to reach to a certain target, the pseudocode snippet may look like this. While you haven't reached it, keep going. But then, the robot sensors like camera outputs the relative movement frame to frame. Say, if the robot moves to the left, it may output the vector like -1, 0, but you want to describe it in the global frame as an observer in the ground station. Then you need this rotation matrix. You can simply multiply a vector to the rotation matrix to convert the same vector, physically same vector, from one frame to another frame. The definition of the rotation matrix is like this. Using sine and cosine, you can convert the vector in one frame to another, but would you be able to imagine this or simulate this for 3D space in your brain? It's quite hard for me, and it actually slows down my brain, and I cannot do this all the time. I think this is why the genius people said that they don't simulate this all the time. Indeed, they are also just plug in the numbers and calculate. Because they understand the motivation and the purpose of using this rotation matrix to convert one frame to another. It's not a big deal. It's just like using an API. Yes, API, Application Programming Interface. If you've ever built a website in JavaScript, you must have used a REST API. For instance, there is Stripe APIs like these, then we just use them without even thinking about what would be happening inside of the Stripe server. We can just do this because we know what kind of information is needed, and the returned information contains our expectation because we trust them. And it's the same analogy for using the rotation matrix. We know what we need, the velocity vector in the global frame, from the body frame from your camera of the robot. Then, if you know what the rotation matrix is doing, you can just use it like an API. Therefore, it's not really necessary to animate the geometric simulation in your head if you only understand the concept of the rotation matrix. So during my grad program, I wondered a lot to understand how these math geniuses process the information. But now, I doubt if they were that special. Probably they were just familiar with this kind of thinking process earlier than me, and that's it. Again, I never say I'm good at math, but for me as an engineer, this is a quite good enough starting point to break through a math illiteracy. Trust me, once you make this kind of breakthrough moment, next barrier will be easier. Just don't let the math give up on you or your career goal. It may be quite easier than you think. Don't give up the math course like me. And like always, if you like this kind of content, please like it and subscribe to my channel if you haven't yet. Your support fuels me to keep uploading this kind of videos. My name is Elliot. I'll see you around.